last talk today is by Rafael.
Oh, you need this one too.
Among the organizers, Rafael did the heaviest lifting. So let's give him a hand.
Thank you, and it's great to be back here and speak at this great event. Happy birthday, Joe, again. So I'm going to talk about cryptography and scientific discovery. This is not based on joint work with Joe, but the idea of kind of combining cryptography with other areas is something that I started doing with Joe. It started 17 years ago, so I've only known Joe. I'm probably the person I've known Joe the shortest among the speakers today. When I came here to Cornell for my interview, and we started arguing about how to define sequential equilibria for analyzing cryptographic protocols. So in cryptographic protocols, you need to deal with agents that are computationally bounded. Cryptography is all about computational limitations. And the question is, how should you define this technical notion of sequential equilibrium in game theory that deals with this? And that's an argument we still have. We've written a few papers about it, maybe 3, 4, and we're still not happy about the current definition, and it's still an ongoing project, and that I think will continue for many more years. So to give you just a little hint of the idea behind that before moving on to this thing, what we tried to do was to create a theory of games that takes into account that players are computationally bounded. So we would like to add a cost for computation. And this would be a way to be able to analyze cryptographic protocols. And so to give a hint of that, let's consider one of the most classic games in game theory. And this is a picture from our first paper that we started in 2006. It took us maybe 4 years. And for those of you who have written papers with Joe, I don't have a slide for it. We write something, and then the next person writes a comment with Joe 1, and then I write Raf 1, and then Joe writes Joe 2. That paper came up to 80. So it means that most sentences have been edited like 4 times on average. But the overall, the paper was, so it took 4 years to finish that paper. Okay, so rock, paper, scissors, the most classic game in game theory. You all know it. Rock beats scissors, scissors beat paper. And so how do we play this game? It's well known. The best thing to do here, and the only equilibrium, Nash equilibrium, is to randomize 1/3, 1/3, 1/3. So you just pick one of these actions at random, you do the same, done. That's what game theory says. Now, people still play this game, right? And actually, not only play it, there's a world championship in this. So how come there's a world champion in the game that has like a textbook solution, page 1 in the game theory book? So what we said is like, look, maybe it's not so easy. Maybe there should be a little cost for randomness, like a little epsilon. Every time you would like to use a random coin, so think of yourself as a Turing machine, and you get access to a coin flip. So you can flip a random coin, and every time you flip a coin, you have to pay a little epsilon. So what happens to this game? With that minor addition, which seems very reasonable, right? It's not free to randomize. Anyone?
But this is not the game that people play in real life.
It is the game. They do it 3 times. Okay.
No, there is temporal dimension, for example, which is when you go into normal form, you start.
No, you're supposed to do it straight away, right?
There is a temporal dimension.
Okay, so let's let's analyze this. What do you think happens if you just take this one, the cleanest, idealist form of the game, but there is a tiny little cost for randomness? What should we do? Actually, nobody knows. Turns out there is no equilibrium. Okay, it's actually very easy to see there is no Nash equilibrium in this game. And the argument is very simple. It's known that there is no deterministic Nash equilibrium here. Okay, so let's assume that there exists a randomized one, where let's say both of us randomize for simplicity. Now in this game, if you have some randomized strategy, turns out that the best thing for me to do is to always play a deterministic strategy. So therefore, if I was supposed to randomize, playing this deterministic strategy is going to be just epsilon cheaper, but it's still cheaper. So therefore, we could not have had a randomized strategy. So what therefore turns out we need to have had a deterministic Nash equilibrium, but it's already known that that doesn't exist. So this simple example shows that just charging a little bit for randomness really ruins everything we know about game theory. The main theorem that natural equilibrium always exists doesn't hold it anymore. And it turned out that was a more complicated part of the paper, that actually that's exactly, the cost of randomness is exactly what determines whether natural equilibrium exists in games with costly computation. When the randomness is free, then we can prove there is always a natural equilibrium, and when it's not free, then it is not the case. Okay, so with this little preamble, let's now switch gears, and somewhat curiously, we'll see that actually this notion of randomness will come back. So I want to switch gears and talk about cryptography, okay, and connect cryptography with scientific discovery.
In the, sorry if this is completely off base, but in the world championship, is there effectively that cost, or is that just something?
No, that is what our stipulation. We are conjecture that maybe that is the way that explains why this is actually, some people the cost is, are better than others, right? Yeah. Okay, cryptography. See, it's the same cycle as rock, paper, scissors. It's something else. So let me summarize cryptography very fast. I'm going to have one slide summarizing the last 2,000 years of cryptography. This is basically the way it's been going on. People or something called an artist would invent some secret code, okay, some scheme that would allow me to communicate securely with somebody else. And maybe this artist would claim that known types of attacks don't work on the scheme. And this scheme would get deployed and in very critical situations until it would eventually get broken. Once it gets broken, we have now learned a new type of attack, and we need a new artist that will come up with a new scheme that prevents against that attack. And that's how things went on and on for the last 2,000 years. We've been stuck in this kind of cat and mouse game between cryptanalysts and cryptographers that were really just artists. So this is what I call the dark ages of cryptography. Renaissance came to cryptography much later, only in the 70s, in 1976, Diffie-Hellman really tried to get us out of this thing. And they came up with a beautiful new concept, that of a one-way function. In their humble paper that started off with, we're on the brink of a revolution in cryptography. Unfortunately, they were right. This was indeed a real revolution. Sometimes you can write those things, but it's only when you write. Yeah. So what did they do? They came up with this concept called the one-way function that they conjectured would be kind of a minimal, kind of like the atom needed for secure cryptography. So what is this? It's a function that's easy to compute, and by easy I mean it can be done efficiently in polynomial time, but it's hard to go back. So given f of x, it should be computationally hard to find back what x is. Okay, so there's no, what's referred to a probabilistic polynomial time algorithm that can invert it. And the most classic example of a conjectured one-way function is multiplication. So multiplying large numbers, we can do it, and even ChatGPT-4 can do it very nicely, actually, beautifully, using schoolbook multiplication. But if I give you the product of two primes, we don't know how to find back what the primes are. And it's believed to be very, very hard. Okay? So given the multiplication is easy, but if I give it a multiplication, we don't know how to go back. Okay, this is a conjectured one-way function, but we don't know if it actually is a one-way function, but we believe so. So Diffie-Hellman kind of conjectured this is really what we need. Secure encryption needs to contain a one-way function, and hopefully, if we have one, maybe we can get secure encryption. And indeed, their kind of prophecy turned out to be exactly right. And in the decades following their paper, it was shown that actually one-way functions are both sufficient and necessary for many of the most classic things that we need and do in cryptography, such as private encryption. So the way we encrypt things on the internet, something called pseudonym generator, digital signatures, authentication, blah, 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 blah. Basically, everything you do when you communicate securely on the internet requires one-way function. And for most of those tasks, also one-way functions are sufficient. Okay, so it's exactly what you need to securely communicate on the internet. So it's safe to say that whether one-way functions exist is the most important problem in cryptography. Without one-way functions, no encryption, no authentication, and so on and so forth. Okay. Let me mention, there are also more advanced tasks in cryptography, like something called public encryption, OT, obfuscation. If you don't know what these are, doesn't matter. But one-way functions is not enough to get those more advanced things. One-way functions are enough to do what's called kind of the basic tasks in cryptography. But those things actually imply one-way function also, except for obfuscation. Okay, so the question is, do one-way functions exist? And indeed, that was a question that Diffie-Hellman clearly asked when he introduced it. And they made one observation: to determine whether one-way functions exist is not going to be so easy. The conjecture do exist, but if you want to prove that they exist, you actually first need to solve another problem, which is the P versus NP problem. Because if one-way functions exist, then we know that P and P is not equal to P. Okay, so this is not proving that they exist is not going to be easy. This requires first proving that NP is not equal to P, so not so easy. And they kind of hope that maybe these problems are the same. Maybe one can actually show that if NP is not equal to P, then also one-way functions exist. That would be kind of the best case scenario. That has today become referred to as the holy grail of cryptography, to show that one-way functions can be based on the hardness of NP. We still don't know how to do it. That would be an awesome win-win for cryptography. That would mean that either we have secure cryptography, or if we don't have secure cryptography, then NP is equal to P, and we can solve all NP problems in polynomial time. Now, not known how to do it. Now, so what do we do if we don't have this holy grail? If you can't base one-way functions on NP not equal to P, what do people do? Well, today we have candidates. We have conjectured constructions of one-way function, like the one I mentioned, based on factoring, multiplication. That's probably most.
Back to the dark ages.
Sorry?
Or back to the dark ages.
Exactly. So in some sense, we're not back to the dark ages, but what Diffie-Hellman's work kind of did was, and the work that followed, is we managed to build these amazing castles, but they're all standing on this pillar of one-way function, and that pillar is based on the dark ages. Basically, there we have candidates, but everything else on top of that, we have beautiful machinery. Right? So we're building all these fantastic creatures, but the pillar is standing on, yes, that we're still back in the dark ages, kind of. Discrete log, lattice problems, and so on and so forth. There's a bunch of candidates, and they're not broken so far, but for how long? And there is this nice quote by Joe Killian quoting Micali, that cryptographers rarely sleep well at night. That's at least what Silvia said, and Joe Killian had the interpretation that the reason he said it was that they're worried that at any moment they wake up and these things could be broken. Now, we talked about causality. This might be a true fact, but not clear whether that was the reason for it. They might not sleep well at night for other reasons. And in particular, if quantum computers get built to scale, then these two guys would be broken. So the most classic examples would actually be broken by quantum computers. The other ones are not, but as you see, this one hasn't been around for that long. So who knows? Some of these things in dark ages actually survived for 400 years until they were broken, and now high school students would break them. So the central problem that we're looking at here is, does there exist some natural complexity theoretic problem that characterizes whether one-way functions exist? So can we get a single problem that tells us, let's focus on this. This is the problem you need to study. Factoring, if we break it, maybe we can go to something else. But no, we'd like to have something that has the property that if you break this, then you can break all encryption schemes. And if this is secure, then you have a secure encryption scheme. Just focus all your attention on this problem. That's kind of like what Diffie-Hellman were after with the NP versus P problem. That one, if you had been able to get one-way functions from NP not equal to P, it would have been complete. So since we can't, can we at least find some other problem maybe that characterizes it? And that's what Janji and I did a few years ago in this work, where we show that one-way functions exist if and only if the so-called time-bounded Kolmogorov complexity problem is hard on average. Okay, so there's a bunch of new words here. So let me explain what they are, and there will be a connection between this and scientific discovery shortly. Okay. So most of you have probably heard about the concept of Kolmogorov complexity, but let me anyway briefly recall it. So the notion of Kolmogorov complexity was independently introduced by Solomonov, Kolmogorov, and Chatin, and it was meant to try to answer the following question. Here you see two strings. Okay, which of them is more random? Well, everyone looking at them can see like, oh, this one clearly is not so random. That one looks random, right? So ostensibly, we can tell this one is not random, this one is. But how can we make sense of that? Because probability theory, classic probability theory would say, well, you need to define some distribution. Which distribution are we talking about? The uniform distribution? In the uniform distribution, they're both as likely. They're both as random, right? Nothing wrong with this one. Happens with probability 10 to the minus whatever the length of the string is, right? Same. So how do we make sense of randomness in individual strings? And the notion of cohomology complexity try to address this thing. And it does so by saying, let's define the complexity of a string as the length of the shortest program that generates the string. Okay. Now you see, the string up here has a short program that generates it. Right? It's just print 1, 2, 3 with a for loop. This one might not have a program that's actually shorter than just print and the whole hard coding the whole string. So you can always, the cohomology complexity of a string is never much longer than the length of a string. It's a string plus some constant. But maybe, you know, there's nothing better. So cohomology's idea was, if something has large cohomology complexity, then I call it random. If it's small cohomology complexity, then it's not random. So this is a fantastic concept, has lots of amazing applications. I think the most beautiful proof of Gödel's incompleteness theorem is through this. You can prove things that have nothing to do with this, like the density of primes has a beautiful proof also using cohomology complexity, and lots of other surprising applications. But it's not computable. It's a great notion, but like if you actually want to use it to check if something is random or not so great, because it's not computable, and that's good if you want to prove an incompleteness theorem, but it's not good if you want to use it. And Kolmogorov noticed this already, okay? And so he also in his paper actually defined the notion of time bundle cohomology complexity, or resource bundle cohomology complexity, which is the most natural thing to do. To say, look, I cannot let a program run forever. That doesn't make any sense. Let's consider a program that runs in, say, polynomial time, or n squared was what he thought was good, okay? So let's consider the same notion, but let's find the length of the shortest program that runs in reasonable time. So in time t, and this is t a parameter, and think of t as n squared or any other polynomial. And now we can ask, can we efficiently compute this? And indeed, that's what Kolmogorov asked, and the people who studied it in the 60s. Indeed, Leonid Levin, in his at least according to the mythology, when he was doing his thesis that introduced this MP and P and this famous MP versus P problem, apparently he delayed publishing this because Kolmogorov asked him, like, okay, it's really good, but you also need to find some, like, you know, some practical problem that's MP complete, not this like circuit sat, whatever that is. Let's, you know, prove that time bounded cohomology complexity is MP complete. And apparently he was trying for a year. He failed, eventually published the thesis anyway. It's still an open problem whether it's MP complete. So we don't know if it's easy to do, and we don't know if it's MP complete. And interestingly, this problem actually was independently, the time-bounded one, independently introduced by Joris Hatmanis here in the 1980s. The reason it's independent was because, of course, there was an iron wall. So the research done in the Soviet Union wasn't known actually here, and at the same time by Sipser and by Co. And the cool thing here is that this is one of the few problems for which we have what's referred to as in Russian the Peribor conjecture. Peribor means brute force. So this is a problem for which no algorithm is better than brute force. That's known. So how hard is this problem? And in fact, you know, if this problem turned out to be easy, what would happen? Well, clearly we can do optimal file compression. We can find a file, find the shortest description of the file, great compression, very nice, but no, it's not changing the world in a radical way. What's more intriguing is, I would say, science becomes easy, at least if you believe Occam's razor. So what does Occam's razor say? If you have two theories that try to explain some phenomena, the simplest one is the most believable one. Okay, so if you would like to, given some data, like to get an explanation for this data, the best explanation actually is the one given by the one that has the smallest Cryptography complexity. So if you not only can compute it, but also can find the program, then this is will give you the best theory that describes this data. So optimal science. Okay. Now there's a little asterisk here because it's still going to be, we still have to work to get the data. Okay, so we'll be the slaves of the computers. We will collect stuff, and it will do all the interesting things.
I'm not sure outcome should be so literally true.
So indeed, there's still a, if we believe this, maybe we shouldn't believe it, but I take this as an axiom in my talk here, that we believe Occam's razor. In the absence of a better foundation for science. Sorry? Yeah.
I thought the point was that like simplest isn't clearly, it's not clear that should be identified with compressible.
So simplest, you need to describe some language. So you can define Cryptography complexity with respect to technically with respect to universal two machine. The universal two machine is a language. So now that gives you a notion of simplicity. It's actually a very robust notion. So. Okay, so to state our result, I actually need to take one extra step. So in the Soviet Union, already in the 60s, they considered the problem of computing this always, but they also said, look, if I don't have an algorithm that does it always, can I do it with high probability? Can I do it for a large fraction of strings? It's quite fascinating. Already in the 60s, this was before average case complexity was studied in complexity theory. They call it the frequential version of the problem. So do I have an algorithm that solves for a large frequency of numbers? So a large fraction of numbers. So that's what we refer to as average case hardness. And let me not say that. Today, we can also talk about computing it over samples that come from any other distribution. You don't have to just look at the uniform distribution. Uniform is, of course, the most natural, in particular for a problem like this. But of course, we can think about also over hardness over other distributions. And now the notion of something being mildly hard on average, or hard on average, is just to say that the problem is hard if there is no algorithm that can compute this with high probability, and high probability is technically defined as 1 minus 1 over polynomial for any polynomial. So I can get arbitrary close to 1. I don't have to get to probability 1, but I can get there to with 99, 99.9, and so on and so forth. Okay, so it's hard if there's no algorithm that succeeds with very, very high probability with it on this particular distribution. Okay, so that's what it means for the question to be hard.
Question.
Yeah.
I don't know if it's related to this or goes back to the Occam's razor. I'm a little perplexed because when you collect all of your data, let's just model it as Gaussian distributed about some means in some multidimensional space. Then with the complexity for printing out that data might be very high if you had to represent all of the random noise that came into it because
yes, so this is, when I'm saying scientific discovery, this is an idealist way when I'm ignoring noise. Let's say I'm getting perfect data. And of course, one should redo all of this also with noise, but it's a starting point. Okay, so I'm now ready to state our first theorem from 2020, which I said gave this characterization of 1-D functions. And it showed the following: 1-D functions exist if and only if KT is mildly hard on average. So if this problem, if there doesn't exist an algorithm that succeeds with very high probability over the uniform distribution, in that case, 1-D functions exist. And this is an if and only if. So if you would like to break all crypto, this is the problem you should focus on. Okay? And if you focus on that problem, you want to do something too hard either. This is exactly the problem you need to focus on if you believe crypto doesn't exist. So as I mentioned, this gives the first natural problem that characterizes 1-D function. Intriguingly, this also, using this treatment, it gave us a lot of new insights into Cryptography complexity that have been open since the 60s. For instance, the question of, is it easier to compute it exactly? Sorry, is it harder to compute exactly than to approximate? right? That's a question that they were discussing. You know, maybe approximating is easier than computing. Turns out, no, they're as hard.
What does it mean to approximate?
You would like to get something that's within log n of a right. Okay. Or another question: is it harder to find the optimal length program than to just determine length? These are these type of decision to search questions. We know it for SAT, but for these type of problems that where there's no structure, it wasn't known. Turns out, yes, they're as hard. And both the answer to these questions actually come out of this treatment with cryptography. So passing through cryptography allows us to give answers to these questions in Kolmogorov complexity.
But if you allow for randomized algorithm, you also go to the pack direction.
No, I don't think it helps us.
Hmm?
I don't know how that can help you. It's still actually an open problem to get a direct proof that doesn't go through one-in functions and a construction of pseudo. Like it's a lot of cryptographic machinery goes into it. We don't know of a direct construction that does this. And it also gives this like nice win-win scenario for cryptography, that either one-in functions exist, that is unbreakable crypto exists, or if it doesn't exist, we now have an algorithm for computing KT, and in fact, not only computing it, but also finding KT witnesses. So that means that now science is easy in this like simplified model of science. So that's kind of the. Now there is a little caveat here. What I've shown here is that one-in functions exist is equivalent to this being hard on a uniform distribution. So what we get here, science becomes easy on the uniform distribution. Okay, so if you give uniform samples of something, but that's not so interesting. You would hope that nature is not just like random strings. We see structure in a bunch of in nature, so maybe for scientific discovery is not such an easy, interesting question. And so, in an upcoming paper that's encrypted in a few months this summer, we actually managed to overcome this thing and show that actually, if you consider a slight version, something called probabilistic KT, and I'll tell you shortly what it is, then you can show that the existence of one-in functions is equivalent to average case hardness with respect to the uniform distribution, but that is also equivalent to average case hardness with respect to any sampleable distribution. So if it's hard on some sampleable distribution, then you have one-in functions. So if you look at the flip side of that, what that means is that if you don't, either you have secure crypto, great. If you don't have secure cryptography, then you can actually you can find KT witnesses on any instance that's been sampled by an efficient process.
Any here means every?
On any sampleable distribution.
Okay, what does any mean? Every?
Yes, every, yeah. So if your data has been collected by a polynomial time algorithm that generates the data, and then you get the labeling of it, in that case, you will be able to find the smallest model for it. Now, of course, if nature is not polynomial time, then we're screwed, and that doesn't help. But if nature is polynomial time, then we'll be able to find the best program for it.
Nature is quantum computer, no?
In that, yes, we'll have to deal with that later. Okay. Okay, this probabilistic KT is not the exact same as KT. It's a different version of it, where you have access to, where your program gets access to a random string for free that you're not being charged for. Your program can access that. Let me not go into this thing. That can also be removed under so-called Nielsen videos under the assumptions and so on. So I'm gonna try to wrap up here. So what we've seen here is that average case hardness of the standard Kolmogorov complexity, time-bounded Kolmogorov complexity problem actually is equivalent to the existence of cryptography. So basically the two fundamental questions in two separate fields actually turn out to be the same. Whether there exists a polynomial algorithm for computer Kolmogorov complexity is actually the same as the question of whether secure encryption schemes exist. And we got this win-win scenario. Either crypto exists or scientific discovery is easy. Now I was teaching this result in a class at a few weeks ago, and I was calling this a win-win scenario, and the students were like, this is not a win-win. This means that there is nothing, either there's no privacy or there's no fun in science. So it's it's a win-lose, but it depends on how you look at things. Another conclusion is that passing through cryptography can give us insight into long-standing open questions in cosmological complexity. And I really think there's a golden time now for these connections. Been an explosion of works connecting now these two fields. And I think there's a lot more to be done. So let me sum up here by attempting to give my cosmological complexity summary of Joe in an as succinct way as possible. I would summarize as apple, yogurt, and Frank Zappa.
You said you were going to leave the quantum computing for later.
No, yeah, for later research. We're thinking about it, yeah.
Question because you didn't enter it. So we could imagine a world in which E is not equal to NP. We don't know where BQP sits.
Yeah.
Exactly. We could imagine a world if we didn't know about BQP, then one-wave functions would exist, including the multiplying numbers. So my question is, does your calculation of the Kolmogorov complexity permit quantum algorithms?
No, well, we don't know, right? But if you find a quantum algorithm for computing Kolmogorov complexity, then you would have been able to break all these other things like lattice problems and all these other things also, because, as I said, that one is actually complete. So it breaks all the. But indeed, if you want to show that quantum algorithms don't just break factoring, but break all crypto and kills off all crypto, then you need to find a quantum algorithm for Kolmogorov complexity. Or prove that, well, yeah, that would be kind of hard. But at least in some idealized model, I think that's a great problem, yeah.
Is there maybe some hope of constructing something practical from it, like actually replacing factoring with some Kolmogorov complexity?
Yeah, no, we're currently actually working on the original construction. I didn't tell you the details of it. It's not practical at all. It's very non-practical, but we have some ideas now that hopefully they can lead to something practical.
Okay, thanks, Rafael.